Download this code from codegive.com, link in the description below. Loop unrolling, a deep dive with Geeks for Geeks examples. Loop unrolling is a compiler optimization technique that aims to improve the performance of a program by reducing the overhead associated with loop control instructions. Instead of repeatedly executing the loop's body for each iteration, loop unrolling replicates the body multiple times within the loop. This reduces the number of loop condition checks, jump instructions, and other loop maintenance operations. This tutorial will explore the concept of loop unrolling, its benefits, drawbacks, different types, and practical examples. We will also delve into the impact of loop unrolling on code size and cache performance. 1. Understanding loop overhead. Before diving into loop unrolling, it's essential to understand the overhead involved in traditional loop execution. Consider a simple for loop. For each iteration of this loop, the following operations are typically performed. 1. Incrementing the loop counter, I++, the value of I is incremented. 2. Checking the loop condition, IN, a comparison is made to determine if the loop should continue. 3. Conditional branching/jump, based on the result of the condition check, the program either jumps back to the beginning of the loop, if IN, or exits the loop. These operations, while seemingly small individually, contribute to a significant overhead, especially for loops with very short bodies that perform minimal computation. The cost of managing the loop control can become a bottleneck, overshadowing the actual computation within the loop. 2. The idea behind loop unrolling. Loop unrolling aims to reduce this overhead by essentially performing multiple loop iterations within a single loop iteration of the unrolled loop. Imagine replicating the loop body k times within a new loop. The new loop will then iterate fewer times, n/k, but each iteration will do more work. For example, unrolling the above loop twice would look like this. Notice that the I variable is incremented by 2 now, I plus equals 2, and we've effectively reduced the number of iterations by half. The key is that the loop condition check and increment occur less frequently. 3. Benefits of loop unrolling. Reduced loop overhead. The primary benefit is the reduction in the number of loop control instructions executed, leading to performance gains. Increased instruction level parallelism, ILP. By replicating the loop body, more independent instructions become available within a single unrolled iteration. This allows the processor to execute these instructions in parallel, if the architecture supports it, further improving performance. Improved cache utilization. Unrolling can lead to better spatial locality, especially when dealing with arrays. When the loop accesses elements that are close together in memory, unrolling can bring more of the relevant data into the cache in a single operation, reducing the number of cache misses. Opportunities for further optimizations. Once a loop is unrolled, the compiler can perform further optimizations within the unrolled body, such as common sub-expression elimination or register allocation, which were previously not possible due to the loop boundaries. 4. Drawbacks of loop unrolling. Increased code size. The most significant disadvantage is the increase in code size. Replicating the loop body increases the total number of instructions, potentially leading to larger executable files and increased memory footprint. This can also lead to reduced instruction cache performance if the unrolled loop becomes too large to fit in the cache. Code complexity. Manually unrolling loops can make the code more complex and harder to maintain. It's important to carefully consider the trade-offs between performance gains and code readability. Potential for register spills. If the unrolled loop body uses too many variables, the compiler might have to spill some of them to memory, leading to performance degradation. Proper register allocation is crucial. Asterisk diminishing returns. Asterisk unrolling a loop too many times can lead to diminishing returns. The performance gains might plateau or even decrease due to the increased code size and register pressure. Finding the optimal unrolling factor is crucial. Asterisk modulus operations / conditional logic. Asterisk as seen in the examples below, unrolled loops may need code to handle cases where the number of iterations is not evenly divisible by the unrolling factor. This added conditional logic can somewhat offset the benefits of unrolling. 5. Types of loop unrolling. There are two main types of loop unrolling. Asterisk manual loop unrolling. Asterisk the programmer manually replicates the loop body and modifies the loop control variables. This gives the programmer fine-grained control over the unrolling process but can be tedious and error-prone. Asterisk compiler-directed loop unrolling. Asterisk the compiler automatically unrolls loops based on heuristics and optimization settings. Most modern compilers are capable of performing loop unrolling. The programmer can often influence the compiler's behavior using pragmas or compiler options. 6. Code examples, manual loop unrolling. Example 1, simple array summation. Let's start with a simple example of summing the elements of an array. Original code asterisk. Manually unrolled code, unrolling factor equals 2. Explanation asterisk. Asterisk we unrolled the loop twice, so each iteration now adds 2 elements to the sum. Asterisk the loop increment is now I plus equals 2. Asterisk we use n1 as the condition in the for loop to avoid accessing arrn when n is even. Asterisk a conditional if statement handles the case where n is odd. Example 2, matrix multiplication, illustrating ILP potential. Consider a simplified version of matrix multiplication. Original code asterisk. Manually unrolled code, unrolling inner loop by 2. Explanation asterisk. Asterisk we unrolled the inner loop twice. Asterisk inside the inner loop, we now perform 2 multiplications and additions in each iteration. Asterisk the outer loop remains unchanged. Asterisk a conditional if handles the remaining element in the inner loop if n is odd. In this example, the unrolled inner loop now has the potential for greater instruction level parallelism. The processor can potentially execute the 2 multiplications and the 2 additions in parallel. However, whether this actually translates to performance gains depends on the target architecture and the compiler's ability to exploit the available parallelism. 7. Compiler-directed loop unrolling. Modern compilers are often capable of automatically unrolling loops during optimization. The extent to which they unroll loops depends on various factors, including asterisk optimization level asterisk higher optimization levels, example 02, 03 in GCC/Clang, typically enable more aggressive loop unrolling. Asterisk loop characteristics asterisk the compiler analyzes the loop to determine if it is a good candidate for unrolling. Factors considered include the loop body size, the number of iterations, and the presence of dependencies. Asterisk target architecture asterisk the compiler takes into account the characteristics of the target processor, such as the number of registers and the availability of parallel execution units. Asterisk loop unrolling pragmas/directives asterisk some compilers provide pragmas or directives that allow the programmer to explicitly request loop unrolling or to control the unrolling factor. Example, using compiler pragmas, GCC/Clang. Explanation asterisk. Asterisk the pragma GCC unroll for directive instructs the GCC or Clang compiler to unroll the loop by a factor of 4. This is just a hint, the compiler may or may not follow your instructions. Asterisk the compiler will then attempt to unroll the loop, replicating the sum plus equals ARRI statement 4 times within each iteration. Asterisk other compilers may have different pragmas/directives. 8. Considerations for optimal unrolling. Asterisk experimentation. Asterisk the optimal unrolling factor depends on the specific code, the target architecture, and the compiler. It's often necessary to experiment with different unrolling factors to find the one that yields the best performance. Use profiling tools to measure the performance impact of loop unrolling. Asterisk loop dependencies. Asterisk if the loop iterations depend on each other, loop unrolling might not be possible or might require careful handling of the dependencies. Asterisk cache size and locality. Asterisk consider the size of the data being processed by the loop and the size of the processor's cache. Unrolling can improve cache utilization if it brings more of the relevant data into the cache, but it can also lead to cache thrashing if the unrolled loop becomes too large. Asterisk code maintainability. Asterisk manually unrolling loops can make the code more difficult to read and maintain. Balance the performance gains with the need for code clarity. If possible, rely on the compiler's automatic unrolling capabilities or use compiler pragmas. 9. When to use loop unrolling. Loop unrolling is most beneficial when asterisk the loop body is small and the loop overhead is significant. Asterisk the loop has a large number of iterations. Asterisk there is an opportunity to exploit instruction-level parallelism. Asterisk cache locality can be improved. Avoid loop unrolling when asterisk the loop body is large and complex. Asterisk the code size is a major concern. Asterisk the loop has many dependencies between iterations. Asterisk you don't have a good way to measure its performance. Asterisk the code becomes much harder to read and maintain. 10. Conclusion. Loop unrolling is a powerful optimization technique that can improve the performance of loops by reducing loop overhead and increasing instruction-level parallelism. However, it's important to carefully consider the trade-offs between performance gains, code size, and code maintainability. Experimentation and profiling are crucial to determine the optimal unrolling factor and to ensure that loop unrolling actually improves performance in a given situation. Modern compilers can often perform loop unrolling automatically, but manual loop unrolling can sometimes be beneficial when fine-grained control is needed. When using manual loop unrolling, always test thoroughly, and prioritize code readability and maintainability.